Good morning. Last two classes we discussed in details the concept of availability or exergy balance in both open and closed system. So we should have a hurried recapitulation what we did, that we appreciated that availability, that is the work potential of low grade energy, is not conserved the way energy is conserved. There is always a destruction or reduction of the availability in any natural process. This was the outcome of the availability balance. And it can be put in this way, that if there is a closed system which executes a process from one initial state to another final state, and in doing so if it interacts with the surrounding in form of the heat and work energy, then associated with that heat and work there is an availability transfer to the system. Now, if we equate or determine the availability at the final state and availability at the initial state, and if we find out what is the net availability transferred into the system, then we see that what we have seen, rather the availability at the final state is not equal to the availability at the initial state plus the net availability transferred in, which it should be if it would have been conserved the way energy is conserved. But it equals to this thing, that means the availability at the final state equals to the availability at the initial state plus the availability, net availability transferred into the system minus the destruction of availability, which equals to the temperature of a reference environment times the entropy change of the universe, and it is termed as irreversibility. For a reversible process this is 0 and the availability is conserved the same way as the energy is conserved. Similarly, if we think of a control volume, in that case what is the difference between a control volume and a closed system? There is a mass inflow and outflow, mass efflux. Then we have to take balance of the energy coming in, associated with that what is the availability coming in and availability going out. These are known as flow availability. In the similar way, we can tell the flow availability at the outlet should be equal to the flow availability at the inlet plus the net availability transferred into the control volume if it was conserved like energy quantity. Net availability transferred in comes because there is an energy interaction in terms of heat and work with the surrounding, but it does not happen so. In the similar line as it is stated in closed system, for closed system this balance is that availability coming out, that means the flow availability at the outlet stream equals to the flow availability at the inlet stream plus the net availability transferred into the control volume minus the destruction, availability destruction, which is the irreversibility, that is T0 times entropy change of the universe. Now, next we recognize that for any natural process, therefore, this destruction of availability is because of the irreversibility, and more is the departure from the reversible process, that means more is the irreversibility, more is the destruction of the availability, and this is gauged or measured by a parameter known as second law efficiency, which we started for different apparatus or different equipment. We started with a different devices, rather work producing device turbine. We will do it again now. But before that, one should know then what should be our target. Our target should be to make the process as close as possible to the reversible process, so that the destruction of availability is minimum. The destruction of work potential of the low grade energy from which our main object is to find the useful work should be minimum, so that always the energy which is available to us for converting into work should have a higher potential than rather you can tell should have as high as potential should be. Then we start with the second law efficiency. That second law efficiency, first part is the repetition. Again I must start second law efficiency. We started with a turbine, hurriedly I will do. If we just recognize a turbine first. Now what is a turbine? Consider an adiabatic turbine. In all practical cases a turbine is insulated, that means an adiabatic. There is mounted on a shaft, so that we get an work at the rate of let per unit mass. In a steady state, as I have told, that everything is done in unit mass. So this is section 1, this is section 2, that is the outlet section, that is the inlet stream, that is the outlet stream. So the gas or air, whatever is the working fluid, comes at section 1 with an enthalpy H1 and goes out with an enthalpy H2. if we neglect the changes in kinetic and potential energies, we know that del W del M, that is the first law or the energy balance for the steady flow open system, is H1 minus H2. If we neglect the changes in kinetic and potential energy, that means we get work out of the difference in enthalpy. So, if at the same time we defined AF1 and AF2, what is AF2? By definition is H minus T0 small s. This is the specific flow availability, sorry, H2, and AF1 is H1 minus T0 S1, this is 2. So, what is then AF2 minus AF1? If I just write this from their definitions, that will be rather AF1 minus AF2 I write, AF1, that will be better, does not matter. So, a minus sign will come, that will be equal to H1 minus H2, AF1 minus AF2, H1 minus H2 plus T0 S2 minus S1. So, it is clear. So, you see that decrease in availability is equal to enthalpy change plus this quantity, but the change in enthalpy is what? Del W del M plus T0 S2 minus S1. So, what is this? This is T0 delta S universe, because it is adiabatic. So, change in entropy of this working system is the entropy change of the universe. Now, if the process could have been reversible, so this part could have been 0, because the entropy change of the universe is 0, obviously. So, in that case we see it is the difference of availability which could have been the work done per unit mass. So, therefore, we see the actual work done, which is the difference between H1 minus H2, is less than the ideal work done, which is equal to AF1 minus AF2, decrease in flow availability. So, therefore, we could have got more work which is equal to the difference in flow availability at the inlet and outlet if the process could have been reversible. And this is gauged by an efficiency known as second law efficiency, which is defined as del W del M, that is the actual work, divided by AF1 minus AF2, that means this, which is nothing but, sometimes we can write this as theoretical work, where this we can write as actual work, and this becomes equal to 1 when process is reversible. This was clear, earlier class we discussed. Now, similar is the case if you consider a compressor. Now, let us consider a compressor. The difference between the turbine and the compressor is that an adiabatic compressor. An adiabatic compressor. Difference between the turbine and compressor is that it is also an work interacting device, but not work producing device, but it takes work. Let per unit mass basis del W del M is the work which is being added to the compressor, and let this is stage section 1 inlet and section 2 outlet. Similar is the case, let H1 and H2 and corresponding AF1 and AF2. Again, from the steady flow energy equation you can write H2 minus H1. Here I am always writing the positive value of del W del M. That means again work is added, so it will be negative. So, if you write it will become H1 minus H2. I am writing in terms of the positive values. Obviously, when work is added, enthalpy will be more at the outlet than at the inlet, provided we neglect the changes in kinetic and potential energy. So, always I write the positive value of the work, and we always recognize before that this is the work taken by the compressor. So, if I tell that, so there is no harm if I write the positive value, that is true. Now, here if you see, if you find out the increase in availability, rather AF2 minus AF1, what is AF2? The similar way, H2 minus T0 S2, and what is this? H1 minus T0 S1. So, this becomes equal to H2 minus H1 minus T0 S2 minus S1. Just the reverse in a sense. Here you see that H2 minus H1 is the work required by the compressor to go from state 1 to state 2, but the change in availability, increase in availability is less than the work required. That means the availability is restricted. If you compare this with your availability balance equation, this is all right. That means the availability here is availability here plus the availability taken in by the compressor, that means del W del M minus some amount which is the I, that means T0 delta is universe. That means in this case the system, this is a compressor, demands more work as compared to that which it could have taken if the process was reversible. If the process was reversible, so that was 0. That means this I can write. So AF2 minus AF1 would have been the work requirement. So therefore we see the actual work requirement is more than the ideal work requirement. In this case, this will go in this side. So therefore here eta 2, the second law efficiency, is written as the work which is needed is more, but the ideal work, that means AF2 minus AF1, that is the ideal work which is less, because it is taking work divided by the del W del M. Del W del M is the actual work required, which is AF2 minus AF1 plus T0 S2 minus S1. You understand? Divided by the del W del M. Clear? This is the way by which we define the second efficiency of a compressor. Make your concept clear at this stage. So if your concept is clear, slowly you write down the equations, you will arrive at the correct answer. Now please.
So if the compressor is not adiabatic.
Compressor is not adiabatic, then the Q quantity will come here, definitely. If the compressor is not adiabatic, very correct. I am just giving a simple case that compressor is adiabatic. If compressor is not adiabatic, then Q term will come here. Then you have to consider that Q is coming or going. In case of compressor, if you do not consider it is adiabatic, then Q may come out. In case of turbine, Q may come out. In case of turbine also Q may come out, or deliberately Q may be given, so it has to be specified. In that case the energy equations will be modified. At the same time the availability equations will be modified. Okay, so availability balance will be modified. This everything we are writing from that concept. So you will see automatically that when there is a heat transfer also, the change in availability will correspond to your availability balance equation. But the definition is same, that is the ideal work, the ideal work requirement by the actual work requirement. Okay, that is left as an exercise. You do it. That if there is an heat interaction, let us consider some heat is coming out from the system, then what it will be? You change this thing. Definition of the availability will remain the same. But then H1 minus H2 simply will not account for the del W del M. Some heat quantity will come in that case. Okay?
Yes, sir.
Next is heat exchangers, non-work producing devices. Let us consider heat exchangers. Heat exchangers. There are two types of heat exchangers which we will read afterwards. One is the mixing type. Let us consider simply, without telling it in terms of the heat exchanger, rather a mixing device. That means two fluids are mixed, 1 and 2, and goes at 3. Let the fluid stream, the flow rate is M1 dot. Let the fluid or the working fluid or the system M2 dot, and it comes at a temperature T1, it comes at a temperature T2 corresponding enthalpy H1. I am interested with the enthalpy only, and this is the 3, and M3 dot with the enthalpy H3. Now, how to define this second efficiency of the process, but or how to analyze this process? First mass balance. There are three things. One is the mass balance, another is the energy balance, another is the availability balance. Availability balance and entropy balance are almost parallel, we have seen. So if these four things can be determined, then one can determine everything. Now let us consider the entire system as adiabatic. That means these two streams comes at different enthalpy, they mix and goes out. So nothing, no heat and work transfer from this entire system. That means if we take this as a control volume, the control volume does not have any work and heat interactions. Then mass balance tells M3 dot is equal to M1 dot plus M2 dot. This is okay. Then what is your energy balance? Energy balance is M1 dot H1, this is the energy coming in, plus this is the. Now here I neglect the changes in potential and kinetic energy, so that the kinetic energy part of the flowing energy I am neglecting with all these streams. Or if it is there specified that one side kinetic energy is very high, whereas the outlet kinetic energy is very low, or between the two streams that there is a large difference between the kinetic energies, then we will have to take into account. But if the kinetic energies are almost same for all the fluids, then we can neglect the kinetic energy part. Must be equal to M3 dot, that is M2 dot coming in Okay, all right, M3 dot into H3. This is all right. That means M1 dot H1 plus M2 dot H, very simple, it's school level, M1 dot plus M2 dot, that means this energy balance. How H will relate to T, that depends upon the characteristic relationship of the property relationship of the working system. So, this is my energy balance, this is the mass balance, this is my energy balance. Okay. This energy balance can be written in this fashion also, M1 dot into H1 minus H3. Let us consider M1 as the hot fluid and this as the relatively cold fluid, but does not matter, you can write is equal to M2 dot this side H3 minus H2. I can write this way also. That means the energy released by one will be energy gained by the other. This is clear from this type of expression. So, you can write this. Now, availability, if you see what it will be. Now, if I write M1 dot, what is AF1? AF1, let us write AF1. AF1 is what? H1 minus T0 S1. What is AF2? AF2 is H2 T0 S2. These are specific flow availability. What is H3? AF3? H3 minus T0 S3. All right. Now, I write the energy availability balance. Now, without writing availability balance, let us write M1 dot AF1 plus M2 dot AF2, okay, minus M3 dot AF3. What is the result? Please tell me what is the result? M1 dot AF1 plus M2 dot AF2 minus M3 dot AF3. So, M1 dot AF3 is M1 dot, what is AF3? AF3 is AF1, sorry, AF1 is which one? H1 minus T0 S1 plus M2 dot, what is AF2? AF2 is H2 minus T0 S2. What is M3 dot? M3 dot is M1 dot plus M2 dot into H3 minus T0 S3. Okay. So, if you now write M1 H1 plus M1 H2, M1 H1 plus M1 dot H1 plus M2 dot H2 and M1 plus M2 dot H2, they cancels each other. They cancels each other. So, I am leaving with minus T0, let us take T0 is constant, minus M1 dot S1, this is minus. So, this is M2 dot S2. So, this is plus M1 dot plus M2 dot S3. What is this? This becomes T0 M1 dot M1 dot M1 dot S3 minus S1 plus M2 dot S3 minus S2. What is this quantity? This quantity is delta S universe. So, you can make it. So, that means T0 into this is the irreversibility rate. That means, if I make an availability balance, I see that availability outlet, that means availability in is equal to plus M2AF2 is M3AF3 plus I dot, or other way that M3AF3, the availability out is the availability in terms of rate minus the destruction. Clear? Okay. Clear? So, that is the availability balance. In this case, now entropy balance also side by side, everything will be clear. Entropy balance is that one, M1 S3 dot, this is the change of the data. If anybody writes this entropy balance, he will be writing M1 dot S3 minus S1 plus M2 dot S3 minus S2 is the delta S universe. That also one can write, where this M1 dot S3 plus M2 dot S3, these are the entropy going out. That means, for a better understanding, one can write this, everything will be very clear, and this is the entropy which came into the system with the flow plus M2 dot S2 plus. That means, always entropy is being added. While it is going out, you take more entropy, that means which is generated. While the exergy or the available is going out, something is being taken from you. That is the concept. So, this is purely the entropy balance. Any way you can write, this shows you a clear picture. Entropy going out is entropy coming in, plus increase in entropy generation. Availability is same thing, availability going out is availability coming in minus the irreversibility. Clear? In this case, how do you define the second law efficiency? Second law efficiency in this case is defined like this. Second law efficiency is defined, second law efficiency in this case is defined like this. We have taken the availability balance here. Can you see this? You can see the availability balance, this you can see the availability balance. Okay. So, let us write the availability balance again. Let us write the, otherwise it is bad. Availability balance, let me write again. What is availability balance? M1 dot plus M2 dot AF3 is M1 dot AF1, again I am writing, plus M2. So small space is the difficulty. That is the availability in minus this. This is the availability balance. Now, if I write the second law efficiency is this case can be written in terms of any of the fluid. Let this is the hot fluid. Sometimes it is written in terms of cold fluid. Let us write this is the cold fluid which has gained the availability, that means M2 dot AF3 minus AF2, and corresponding loss of availability by the hot fluid is AF1 minus AF3. This is the definition. So, this is the definition, that means the availability increase in the cold fluid divided by the availability decrease in the hot fluid. If you transfer it, you see there is a term irreversibility will come into picture. That means this is the gain which is less than this by the amount irreversibility. If you transfer here M2 dot AF3 minus M2 dot AF2, it will be M1 dot AF1 minus M1 dot AF3 minus I dot. That means it will be this thing, let this thing is x minus I. That means the availability released by this fluid, if I consider this as the hot fluid, this is the convention. We define it in terms of the cold fluid, that is not being taken by the cold fluid. Cold fluid availability gain will be less than that released by the hot fluid. This way we define the second law efficiency for heat exchangers. This is a mixing type. There may be non-mixing type, that the masses are not mixed, they go separately with a separating wall. That will be clear if we solve a problem. Now, very one interesting problem. Now, after this I like to place before you. So, after all these things, I think we are in a solid position. Our understanding, I hope, is very clear. So, we are in a solid position to solve the problems. Let us consider a problem. An adiabatic turbine receives a gas, an adiabatic turbine receives a gas whose properties are given Cp, Cv, and this type of gas always you take H is equal to Cpt, that is not given in this problem. You can take if it is required, I do not know, at 7 bar and 1000 degrees Celsius. These are the important things. And discharge is at 1.5 bar and 665 degrees Celsius. Determine the second law and isentropic efficiencies. Very important. What is the difference between second law and isentropic efficiency? Okay. Just a minute. Second law and isentropic efficiency. So, what are the second law and isentropic efficiencies of the process of the turbine? That means of this process in the turbine. Take T0 this, that is the environment temperature, and it is already given for the problem Cp dt, and PV you take RT, where R is Cp minus Cv. So, what is this problem? Now, let us draw the sketch. The problem is like this. There is a turbine. There is a turbine, adiabatic turbine, okay, which gives del W del M is the work. It is coming at section 1, the working fluid goes at section 2, that is 1 and 2. Okay. Then What is the value of del W del M? Del W del M is H1 minus H2 per unit mass basis I am doing, and H is given dH Cp dt. That means I can write Cp into T1 minus T2. What is T1? 1000 degree and 665 degree. I can write in terms of Celsius because it is the difference, and Cp values equals to, what is the value of Cp given? 1.09 kilojoule per kg, K, 1000 minus 665. Okay. So, this comes out to be, let me see, this comes out to be 365.15 kilojoule per kg. So, per unit mass basis I find out what is the actual work done. Now, what is the ideal work done, or AF2 minus AF1, AF2 minus AF1, sorry, I am sorry, AF1 minus AF2, what is that? AF1 minus AF2 is 365, already we have seen 0.5 plus, which could have become if the process was reversible, plus T0. What is T0? T0 is 298 into delta S universe. Delta S universe. What is delta S universe? Is the delta S of the system. So, delta S of the system in this case, if we have to find out, you have to use this equation. TdS is, why I am writing this not du plus PdB? Because it is better to write in this fashion. You can write TdS is du plus also, does not matter, I write both this. So, if you write this, then ds is dH by T minus V by T dP. dH is Cp dt, that means delta S is Cp ln T2 by T1 minus what is V by T? PV is equal to RT. That means R by P, R is Cp minus Cv. Okay. Ln, one can write, one can find out by this expression. If we equate this, this will be.
Sir, not R by P, sir. Just R.
I am extremely sorry. Very good. You are following nicely. So, I am very happy. Cv ln T2 by T1, and what it will be? Plus R ln V2 by V1, and these two expressions are identical. Well, so any of these two equations I can. So, here if you calculate, T2 is what given? 665 degrees Celsius, corresponding to that you can find out what is the absolute temperature. T1, P2, P1 ratios, so you can put in any unit 7 and 1.5 bar accordingly, and you put it and get the value AF1 minus AF2 will be equal to what? 381 point, that means this comes out to be 16.5 kilojoule per kg. So, this will be 385, just let me see, I have done it, 381.65. So, what is second law efficiency, please? Second law efficiency will be 365.15, 381.65, and that comes out to be 0.956. We have already done it, very good, 0.956. But what is isentropic efficiency and what is meant by this? That is the only thing, because this evaluation of second law efficiency is a routine job, as we have already applied this thing in general for a turbine compressor. So, it is a routine job by putting the numerical values. Now, what is isentropic efficiency? Now, isentropic efficiency concept is like this. This is a turbine. It comes at state 1, it goes at state 2. Isentropic efficiency will come afterwards in the cycle analysis, I will tell you, but now let us, this state 1 is fixed, state 2 is fixed, this is the turbine, and we get a work del W del M. Now, isentropic efficiency is like this. If I plot a TS diagram, let us consider this is the constant pressure line P1, let us consider this as a constant pressure line P2. If we consider this as a gas, either a superheated vapor or air or any gas where the constant pressure line looks like this. So, this is my, rather to understand this, I think it will be better if I use, this is my state 1, and this is not, this is adiabatic, but this is not a reversible process. That means adiabatic reversible hone se kya hoga, this will be isentropic, otherwise it is not isentropic. Now the question comes, it is isentropic means it will be vertical. If it is not isentropic, that means a natural process, that means an irreversible adiabatic, then from the figure or the graph it can be either this side or this side healing, but it cannot heal on this left side. This is because the entropy will decrease of the system, which will lead to the decrease in the entropy of the universe, since the process is adiabatic. So entropy change of the surrounding is 0. So therefore the only solution is that the entropy of the system will increase. Okay, that is because of the internal irreversibility. So that the process is like this. So this is the N2. Now what we have considered here in the second law efficiency, that between the same state point 1 and 2, if we could have considered hypothetically that irreversibility part is 0, then the efficiency which I arrive is the second law efficiency. It is very difficult to understand, I am telling you, think yourself so that you can understand. So that means this difference is very subtle, that this between the second law and the isentropic efficiency. Second law efficiency is that we fix these two states, but there is an irreversibility between the two states. If irreversibility could not have been there, but the system state is 2, that means we are finding out AF1 and AF2 difference, that we are telling the AF1 minus AF2 is the ideal work, provided the system comes from state 1 to state 2. It is a theoretical abstraction or theoretical concept, because this availability is always designated to the state point, though it is a composite property, but if we consider the environment fixed, that this composite property becomes a function of the state points of the system. So when the two states are fixed, then AF1, AF2 are fixed, and their difference is the ideal work. Understand? That means the work which could have been obtained if we discard the irreversibility, for the process connecting the same state points. But now if I consider another picture, that this system starts from same initial state, but it goes under a reversible adiabatic process. If we consider a reversible adiabatic process or isentropic process with the same initial state, then this process could have ended here, not there. That means this is the ideal process. That means if the process could have been ideal, we give a relaxation on the final state point. Very important, no book has defined this thing. I am telling you, you will not get such a lucid explanation in any book, the difference between second law and isentropic efficiency. If we are not bothered about the final state point, but if we consider that for the same initial state point, what could have been the final state point if I could have made a reversible adiabatic process, then the work output of this process del W del M by the blacking, if I consider this as the work for the isentropic process, let I, then the isentropic efficiency is del W del M, the actual del W del M divided by del W del M I. Now how to find out the work done in this process? That means the same initial state, but a reversible adiabatic process which ends up to a different state, then we have to find out this S2 and corresponding H2. You have understood? So how to find out this S2? Please tell me. That means we will have to find out this T2. That means S2 means the change of the entropy of the universe will be 0. That means the change. How to write the change of the entropy of this thing? That is, we can write delta S universe is equal to, let us consider the DH, that means Cp 1 point, what is Cp? Please dictate me, 1.09 into ln T2 by T1, that T2 I don't know, T2 by T1, T1 I know, what is T1? 1000, that means 1273, minus R ln between the same pressure, so pressure ratio remains the same, remains fixed, that means ln 1.5 by 7. This gives you a temperature T2, let me tell you, I have done it. This gives you a temperature T2 which is equal to 891 point, I am sorry, there is a problem. What was your temperature there? Cp ln T2 by T1 Well, this T2 has to be more than this. So, there may be a calculation mistake. What was the T2? In this case, isentropic expansion to 665. Oh, sure. No, that is correct. This is 891. I am sorry. 891.58 K. Yes, that is less than this. So, correct, because this is 665 degrees Celsius. So, this T2 is 665 plus 273 K. So, you understand now, the concept is clear. So, this T2 comes out to be this. Clear? That means the del W del M I will be then H1, now I 2 dash, because this is 2, H1 minus H2 dash, which becomes equal to Cp into T2 dash minus T1, because the property relationship is dH is Cp dt. We can find out this delta W, del W del M, and this becomes isentropic work. So, that becomes equal to 415.75 kilojoule per kg, and accordingly eta 2 is 365.15, this one, divided by 415.75, which becomes equal to 0.878.
So eta 2 is isentropic.
Sorry, eta I. So, clear? Now, isentropic efficiency and the second efficiency, they are proportional to each other. Both of them are the measure of the departure from the reversibility, but it is visualized to different concepts. There is nothing great in it, just the way we characterize it. Sometimes we characterize it with the same end state points by this formula, that is eta second law efficiency, or we characterize the process in this way, that if for the same initial state within the same pressure ratio there could have been an isentropic process, what could have been the end point and what could have been the ideal work, and that way we gauge the departure from reversibility and define that parameter as the ratio of these two works, that is the actual work by ideal work, as the isentropic efficiency. It's clear? Okay. Next, another very simple problem. After this conceptual problem, we should have one very simple problem. You just see this problem. In a counterflow heat exchanger, oil whose property values are given, oil at Cp is 2.1 kilojoule per kg is cooled from 440 K to 320 K. This is a problem of heat exchanger. While water is heated from 290 K to a temperature of T, unknown temperature, and this is a heat exchanger where there is a separation, they do not mix. The respective mass flow rates of oil and water are 800 and 3200 kg per hour. Neglecting pressure drop, these are the usual assumptions. If they are not given, you will assume this. There is a steady flow process, so pressure drop we will neglect. If there is a fluid, incompressible fluid flowing steadily through a duct, so pressure drop is only because of the viscosity. So, one can neglect that viscous pressure drop within a short length of duct. This is the practical thing. So, changes in kinetic and potential energies and heat loss from the heat exchanger. That means there is no heat loss from the heat exchanger. That means the transfer of heat is between the two fluid, oil and water. Determine the temperatures T, the rate of exergy destruction, the second law efficiency. Take the environment temperature. It is a straightforward application for the definition of second law efficiency or application of second law efficiency in a heat exchanger. So, let us think of this problem. You have taken the problem. Okay, I am drawing this line diagram, block diagram, then it will be clear. Not necessarily always you will have to take in language. However, again I am repeating, in a counterflow heat exchanger, oil specific heat at constant pressure 2.1 kilojoule per kg is cooled from 440 K to 320 K, while water specific heat at constant pressure 4.2 kilojoule per kg is heated from 290 K to a temperature T, unknown temperature, which you have to find out. The respective mass flow rates of oil and water are 800 and 3200 kg per hour. Neglecting pressure drop, changes in kinetic and potential energies and heat loss from the heat exchanger, determine the temperature T, well, the rate of exergy destruction in the process, the second law efficiency. All right, giving the reference ambient temperature. So, first of all we must draw the figure here. This is the heat exchange. It is divided into two partitions. Let in this there is a coil for the oil. Let oil goes in this direction. This is the inflow. Counterflow means they go in the opposite direction. They are parallel, flowing parallel, but in the opposite direction. Water going out. Let m dot O is the mass flow rate of oil, it is the mass flow rate of water. They remain same from the conservation of mass. Entire thing is adiabatic. Very simple problem. Okay. Now, this let this section is 1, this section is 2, this is 3, 4. So, 1 pertains to the inlet of oil, 2 pertains to the outlet of oil, 3 pertains to the inlet of water, 4 outlet of water. So, this T1, T2, T3 given, T4 has to be found out. T4 is T to be found out. T1, T2, T3 are given. I am not writing it again. Now, write the energy balance equation. What is the energy balance equation? Write the energy balance m dot O H1, this is coming in, and plus m dot W H3 must be equal to, leaving out, m dot O H2 plus m dot W H4. Okay. In this problem we have to consider again the same thing, that dH is Cp dt. That means dH is Cp dt for the water also, water and oil, that is a fluid. So, therefore, we can take in one side Cp into T1 minus T2, H1 minus H2 is equal to m dot W, that is Cp oil and Cp W into H4 minus H3, that means T minus T3. Everything is given, T1 is given, m dot O is given, Cpo is given, Tw is given. We may not convert the unit in kg per second, we may put it in kg per hour, because this will cancel each other, all in the consistent units. So, we can find out the T. Everything is given, Tw, no, sorry, I am extremely sorry, this will be T minus T3. I am sorry, T3. Okay. So, value of T will be what? 305 K. This school level thing. Clear? Enthalpy coming in, that means the energy coming in with oil, with water, these are the energy going in. Because there is no heat work interaction, changes in kinetic potential energies are same, are negligible, and this is going out. So, I bring it in one sense, dH is Cp dt. So, therefore, H1 minus H2 is Cpo T1 minus T2 and H4 minus H3 is Cpw T minus T3. Clear? So, now how to find out? Tell me the, now if you are lucky, you are not told to find out the change in the flow availability, because calculation will be little more, but if you are asked to find out the irreversibility or what, rate of exergy destruction, that means A dot, destruction of A dot, that is exergy destruction, which is nothing but I dot, which is nothing but T0 delta S in U. So, we do not bother to find out the availability at the terminal points and make an availability balance is not required. You can simply write that from the availability balance concept, we know the rate of destruction of the availability is the rate of irreversibility, which is T0 into delta S universe dot. What is delta S universe dot? Delta S universe dot. It looks better if you write in terms of rate of generation of entropy, which is oil is from 1 to 2, that means this is delta S dot oil plus delta S dot water. So, that is m dot O Cpo ln, then you tell ln T2 by T1. So, what is T2? 440 plus, oh 320, yes, now it is cooled, 320, yes, 320 plus, 320 no plus, 320 is in K, sorry, 440. And what is this? m dot CPW ln T. T is 305 and T1 200. 290. So you find out this, and I dot is T0 sigma dot, and the value is what? The destruction in the availability, that value will come 41.4. If you do not convert here also per hour, then this rate will also be in the same time unit. 41 does not matter, megajoule per hour. Why unnecessarily you convert it? There is no need. Nobody has asked this question, just like a primary school boy, that okay, you find out the I dot in terms of joule per second. So if it is not told, then let us find it in terms of hour. And second law efficiency. How to find out second law efficiency? Second law efficiency here, the same way we can find out that m dot water into AF3 minus, sorry, AF4 minus AF3 divided by m dot oil into F1 minus AF2. Very good. Then you can find out the second law efficiency will be equal to 10 point, very poor, 10.9%. So you see, this heat transfer through a very, very finite temperature difference incurs such an irreversibility loss, 10.9%. This is the definition of this second law efficiency. Okay? You can express one in terms of the other through this, because this will be this minus I dot. So that only one you can calculate only this one, because since the I dot is calculated, you can make the calculation. It does not matter. Anyway you can do it. Clear? Please tell me, this concept is clear? So I can expect that you can solve any problems in availability. Now I will start a new chapter. Today I could have left you, but you see this is a studio class where I cannot leave you before 1 hour. So let us start the next one, the important property relations. Important thermodynamic property relations. Important thermodynamic property relations. Important thermodynamic property relations. Now let us find out what we have known up to the date. Now we know that this thing, you know, TdS is equal to du plus PdV. This is the property relation we know, and at the same time this can be written in a form du is equal to TdS minus PdV. Can I not write this dH TdS? This was discussed earlier also, BDP. Where from it comes? H plus, very good. So you are more knowledgeable than me. H is equal to U plus PV. So from there we can find out du plus PdV is TdS plus VdP. Now first I will introduce two new property now. One is, before going to that, one is Helmholtz function. To new property. I told you that any jugglery between the properties will be another property, but just like that we cannot define a number of millions properties. This must have a physical significance. The way U plus PV, not like that U plus PV has been made like that, a combination U minus PV or U by PV does not bear any physical sense, but U plus PV, you see, has an enormous physical significance, that enthalpy. Similarly, Helmholtz function F is defined as U minus Ts, such a combination, and Gibbs function, these are the name of the scientist who discovered it, Gibbs function H, very good, H minus Ts. So I think that some physical significance have to be told at the moment, otherwise you will not feel interested. For mathematical operations it is enough to know the definition mathematically that F is U minus Ts, G is H minus Ts, the way we define the enthalpy U plus P. Now, this Helmholtz function, if you recollect that our availability, that is the maximum work, is some phi at any state minus phi 0. You understand? Where phi is u plus p0 v0 minus t0 s, and phi 0 is corresponding to that u0 plus p0, sorry, not v0, p0 v0 minus t0 s0. So, this is our availability function, which is a composite function or a composite property of system and surrounding. Why? Because this p0 is there, t0. Now, this p0 part, if I neglect, that means if I consider that the system, the work which is being done, the work to compress the surrounding I neglect, or I consider a system whose pressure and temperature is same as that of the surrounding. But you can tell, sir, it is the single component system, then both the properties are same, that means they are in the same state and that is a dead state. So, nothing will happen. So, therefore, I relax this, I consider the system temperature T0 if any process be same as that of the environment, and system performs a process isothermally, that means the temperature remaining the same, then this T0 can be written as simply temperature of the system. You understand, temperature of the system, because temperature remains constant and that becomes equal to the temperature of the environment. So, I can express a property of the system which is F, let me denote it by F, which is u minus Ts, whose physical significance is that the changes in this function represent the maximum work, reversible work, that we can obtain from a closed system under an isothermal condition, where the constant temperature of the system equals to that of the surrounding. You understand? That means it is the again I am telling, then you will ask, it is the maximum work obtained. It is the maximum work obtained along with the non-useful work, unuseful work. That means inclusive of the displacement work obtained by a system. This is a concept. You try to think, if it executes an isothermal process, means that constant temperature, and that temperature equals to the environment temperature. You understand? For example, when I equate PdV, sometimes I tell at a constant pressure process this becomes is equal to d of PV. Though pressure is constant, so this and this is the same thing. Similarly, if the temperature of the environment and temperature of the system remains same throughout, that means we can take T0, we can replace T0 as T. That means one can tell, sir, it is u minus Ts. That means if I know the system property, I can find out. So, surrounding has not to be spelled out. You understand? If I tell that a system has got this internal energy, this entropy and this temperature, and it comes to a state where this is the internal energy and the same temperature this, and the entropy this, and the surrounding has a temperature of this which is same as the system temperature under isothermal condition, then though the surrounding temperature is given, but only thing that I have to take into mind that system temperature and surrounding temperature is same, then we can tell it is the difference between the Helmholtz function which gives the reversible work or the maximum work in that process. You understand? And this is very, very important in chemical reactions, reaction process which takes place at constant volume where the isothermal condition is maintained. So, this is not beyond the scope of our study here, how this Helmholtz function is being used. Similar is the case in the Gibbs function, but it is with respect to a control volume or open system. We have seen in open system what is the availability. A is H minus T0 S. Changes in this function, it is a composite function. Composite function, because T0 is there, not only of the system. A change of this is responsible for the maximum work, reversible work by a particular by a particular system at a different state flowing through a control volume. All right. Now, if I consider that this system is an isothermal system, the process is an isothermal process, and the working system maintains the isothermal condition where the end and the initial temperature remains the same, throughout the temperature remains same, and that becomes equal to the environment temperature, reference environment temperature, then I can replace T0 as Ts and can define a property or function which is a property of the system only, that is the Gibbs function. That means we can tell that Gibbs function is the maximum work available from a control volume for a given state of its working system at the inlet, okay, provided the process is isothermal and the temperature, constant temperature equals to the surrounding temperature. You understand? All right. For example, again I am telling, if I have a control volume, if I have a system at state 1, system at state 2, no isothermal condition, no constant pressure, no, that is general case, then I can tell that the maximum work which we can get is the difference between the two functions at outlet and inlet, which are the composite functions of system and the environment, where only temperature of the environment comes into picture. What is that? H minus T0s is that function. That means H1 minus T0S1, H2 minus T0S2, difference of these two. But if I tell that similar thing but with a added restriction or constant, that the process is isothermal and that temperature equals to the temperature of the surrounding, you understand? In that case, the maximum work which we could obtain is the difference between Gibbs function, which is purely a system property, not the composite environment property, because it does not matter environment temperature or system temperature, they are same. And this is very important in a constant pressure reaction process, where the reactor is continuously cooled to the ambient temperature or a fixed reference temperature and the reaction takes place in an isothermal process. So, there the availability loss or what could have been the maximum work obtained from a chemical reaction, no work is obtained, but we are interested in finding out the destruction of the availability or exergy in this chemical reaction. So, there the difference in Gibbs function gives you that concept. It is clear? So, this physical concept I think enough for our class, because we are not going to implement this in the physical processes, because this is beyond our scope, this difference in Helmholtz or Gibbs function, but for the time being this a physical understanding is okay. We should only remember this formula that F is equal to U minus Ts, that is Helmholtz function, and G is equal to H minus Ts. So, we add two extra property. Now, what is dF, what is dG? Please tell me. dF is equal to du minus Tds minus Sdt. What is du? du minus Tds is minus Pdv. So, this is minus Pdv minus Sdt. What is dG? dG is equal to dH minus Tds minus Sdt. What is dH minus Tda is Vdp, minus Sdt. So, these four relations are the very basic relations, property relations of thermodynamics, from which we will derive many important and interesting relations afterwards in the next class, because time is up. So, we will start from this point, that means four properties: internal energy, important property, enthalpy, Helmholtz function and Gibbs function are expressed in terms of their differentials in terms of other two properties. Okay? So, up to this today.